You have 10 million document embeddings. A user searches for something, and you need to find the 10 most similar vectors in under 50 milliseconds. Brute force means 10 million comparisons. That's way too slow. So how do vector databases actually do it? The answer is HNSW, Hierarchical Navigable Small World Graphs. It's the algorithm behind every major vector database. And it's built on a surprisingly simple idea: small world networks. You've heard of 6 degrees of separation. Any 2 people on Earth are connected through at most 6 friendships. That's the small world property. In these networks, you can reach any node from any other node in very few hops. HNSW exploits this exact principle for vector search. Think of it like navigating from Mumbai to a specific street in Bangalore. You don't check every street in India. Instead, you take a flight to Bangalore. That's a long-distance jump. Then a cab to the neighborhood. Then you walk to the exact lane. HNSW works the same way. HNSW builds a multi-layer graph. The top layer is sparse, just a few nodes with long-range connections like express highways. The middle layers add more nodes with medium-range connections. And the bottom layer, layer 0, contains every single vector with short-range local links. When a query comes in, search starts at the very top layer. The algorithm does a greedy search. Look at your neighbors. Jump to whichever one is closest to the query, and repeat until you can't get any closer. Then drop down one layer and do it again with more nodes and finer connections. Here's why this is so fast. Instead of comparing against all 10 million vectors, you check maybe 5 to 10 nodes in layer 2, 20 to 50 in layer 1, and 100 to 300 in layer 0. That's around 200 to 400 total comparisons out of 10 million. That's O of log n instead of O of n. Building the index is straightforward. Each new vector gets randomly assigned a layer level. Most end up only in layer 0. A few reach layer 1, even fewer reach layer 2. This follows an exponential distribution, naturally creating the sparse to dense hierarchy. There are 3 key parameters you need to know. M controls how many neighbors each vector connects to. More connections mean higher recall but more memory. Construction controls index quality during build time. And search is your runtime speed versus accuracy knob. And here's the key trade-off. HNSW is approximate, not exact. But look at these numbers. With search at 200, you get 99% recall at just 15 milliseconds, compared to 500 milliseconds for exact search. For most applications, that's indistinguishable from perfect. But HNSW has a catch: memory. The entire graph lives in RAM. For 10,768 dimensional vectors, that's about 30 gigabytes for the vectors plus 2.5 gigabytes for the graph edges. Around 32.5 gigs total. That's the price you pay for speed. Every major vector database uses HNSW as its core, but each adds its own optimizations. Adds quantization and on-disk storage. Has a proprietary modified version. Uses dynamic values. Chroma wraps the open source and brings it right into SQL. Want to try it yourself? Just pip install and, in about 10 lines of Python, you can index 10,000 vectors in half a second and query in 0.1 milliseconds. The code is shockingly simple for how powerful the algorithm is. So remember, HNSW is the algorithm for vector search. It works like navigating a city. Start with highways, end with local lanes. Its approximate but 99% recall at 10x speed is a trade-off worth making every time. Next up, episode 18 on vector databases, where we'll see what gets built on top of HNSW.